In electrical systems utilizing transformers, understanding proper grounding and bonding techniques is crucial for safety and code compliance. When dealing with a transformer such as a 2500 kV ampere pad mount transformer with a primary voltage of 12,470 volts and a secondary voltage of 480/277 volts, specific considerations apply to the neutral connection. The question revolves around the presence of a strap within the transformer that connects the neutral point to the transformer's enclosure or grounding system. The primary concern is whether this strap should remain connected when a separate bonding connection has already been established at the switchboard. The answer is yes. If the neutral is bonded in the switchboard at the neutral bar, the strap in the transformer can remain in the disconnected position. The purpose of the strap in the transformer is to provide a connection between the transformer's neutral point and the grounding system. However, since a separate bonding connection has been established between the neutral bar in the switchboard and the grounding system, the strap is no longer necessary. The rationale behind disconnecting the strap centers on several key benefits. Firstly, improved safety. Secondly, code compliance. Thirdly, reduced overheating. Disconnecting the strap reduces the risk of parallel paths for ground fault currents, which can potentially lead to dangerous overcurrents and equipment damage. Parallel paths for ground fault currents can create unintended routes for current to flow back to the source. This can result in higher than expected currents in these paths, potentially exceeding the ampacity of the conductors and causing overheating or even fires. By ensuring that the ground fault current has a single, well-defined path back to the source, the protective devices, such as circuit breakers or fuses, can operate effectively to clear the fault. The National Electrical Code, commonly referred to as the NEC, typically requires that the transformer's neutral point be bonded to the grounding system at only one point. Connecting the strap in the transformer would violate this requirement. Multiple bonding points can create circulating currents and increase the risk of ground loops. These ground loops can introduce noise into sensitive electronic equipment and create potential shock hazards. The NEC aims to minimize these risks by specifying a single point of bonding for the transformer neutral. Disconnecting the strap eliminates the potential for overheating at the connection point between the strap and the neutral bar due to ground fault currents. When ground fault currents flow through multiple bonding points, the current can concentrate at the connection points, leading to excessive heat. This heat can damage the connections, reduce their effectiveness, and potentially create a fire hazard. By limiting the bonding to a single point, the ground fault current is more evenly distributed, reducing the risk of overheating at any one connection point. Before disconnecting the strap, it is crucial to ensure that the bonding connection in the switchboard is properly established and meets all applicable electrical codes and standards. This includes verifying that the grounding electrode conductor is of the correct size and material, and that it is properly connected to the grounding electrode system. The grounding electrode system typically consists of items such as the incoming water pipe, building steel, and concrete encased electrodes, commonly known as rebar. In a typical installation, the service entrance conductors consist of multiple paralleled conductors, such as 8 paralleled 500 MCM copper conductors, along with a full-size neutral conductor. These conductors feed a main breaker, such as a 3000 amp main breaker, which then distributes power to various fusible branch feeders. The bonding connection at the switchboard is established by running a separate grounding electrode conductor from the neutral bar to each of the following points. Firstly, the incoming water pipe. Secondly, the building steel. Thirdly, the rebar steel in the footer of the building. The size of the grounding electrode conductor is determined by the size of the service entrance conductors, as specified in the NEC. For example, NEC Table 250.66 provides guidance on the minimum size of the grounding electrode conductor based on the size of the service entrance conductors. In this case, with 8 parallel 500 MCM copper conductors, the equivalent area would need to be calculated to determine the appropriate size of the grounding electrode conductor. A 3/0 copper conductor may be sufficient, but it is essential to verify this based on the NEC requirements. It is important to note that the bonding connections to the water pipe, building steel, and rebar steel must be made in accordance with the NEC. This includes ensuring that the connections are mechanically secure and electrically conductive. The connection should also be accessible for inspection and maintenance. The NEC provides specific requirements for the types of clamps and connectors that can be used for grounding and bonding purposes. These requirements are designed to ensure that the connections are reliable and will not corrode or loosen over time. In addition to the grounding electrode conductor, an equipment grounding conductor is also required to be run with the circuit conductors to each piece of equipment. The equipment grounding conductor provides a low impedance path for fault current to flow back to the source, allowing the overcurrent protective devices to operate quickly and clear the fault. The size of the equipment grounding conductor is determined by the size of the overcurrent protective device, as specified in NEC Table 250.122. For example, for a 3000 amp main breaker, the equipment grounding conductor would need to be sized accordingly. It is also important to ensure that all metal enclosures, such as switchboards, panel boards, and junction boxes, are properly bonded together and connected to the equipment grounding conductor. This helps to create a continuous low impedance path for fault current and minimize the risk of electric shock. The NEC provides specific requirements for bonding metal enclosures, including the use of bonding jumpers and bonding bushings. The use of appropriate overcurrent protective devices, such as fuses and circuit breakers, is also crucial for electrical safety. These devices are designed to interrupt the flow of current in the event of an overload or short circuit, protecting equipment and personnel from harm. The selection of the appropriate overcurrent protective device depends on the ampacity of the circuit conductors and the characteristics of the load. The NEC provides guidance on the selection and coordination of overcurrent protective devices. It is essential to ensure that the overcurrent protective devices are properly installed and maintained, and that they are tested periodically to verify their proper operation. Regular inspections and maintenance of the electrical system are also important for ensuring its continued safety and reliability. This includes inspecting conductors for signs of damage or deterioration, tightening connections, and testing grounding and bonding connections. Any deficiencies that are identified during inspection should be promptly corrected. Qualified electrical personnel should perform all electrical work in accordance with applicable electrical codes and standards. This includes obtaining the necessary permits and inspections, and following safe work practices. Proper training and experience are essential for ensuring that electrical work is performed safely and correctly. In summary, disconnecting the neutral strap in the transformer is generally acceptable and often recommended when the neutral is already bonded at the switchboard. This practice improves safety, ensures code compliance, and reduces the risk of overheating. However, it is essential to ensure that the bonding connection at the switchboard is properly established and meets all applicable electrical codes and standards before disconnecting the strap. Regular inspections and maintenance of the electrical system are also crucial for ensuring its continued safety and reliability. When working with electrical systems, it is always important to consult with qualified electrical personnel and follow all applicable electrical codes and standards. This helps to ensure that the work is performed safely and correctly, and that the electrical system is properly protected. The information provided is for general guidance only and should not be considered a substitute for professional electrical advice. Always consult with a qualified electrician or electrical engineer for specific recommendations regarding your electrical system. The NEC is a comprehensive document that provides detailed requirements for electrical installations. It is essential to be familiar with the NEC and to follow its requirements when performing electrical work. The NEC is updated every 3 years, so it is important to ensure that you are using the latest edition. In addition to the NEC, other codes and standards may also apply to electrical installations. These may include local building codes, fire codes, and utility company requirements. It is important to be aware of all applicable codes and standards and to follow them when performing electrical work. Electrical safety is a critical concern, and it is essential to take all necessary precautions to protect yourself and others from electrical hazards. This includes wearing appropriate personal protective equipment, such as gloves and safety glasses, and following safe work practices. Never work on electrical equipment that is energized unless you are properly trained and authorized to do so. Always to energize and lock out electrical equipment before performing any work on it. If you are not comfortable working on electrical equipment, it is best to call a qualified electrician. Electricity can be dangerous, and it is important to respect its power. By following safe work practices and consulting with qualified electrical personnel, you can minimize the risk of electrical accidents. The principles of grounding and bonding are fundamental to electrical safety. Grounding provides a low impedance path for fault current to flow back to the source, allowing the overcurrent protective devices to operate quickly and clear the fault. Bonding ensures that all metal enclosures and equipment are at the same potential, minimizing the risk of electric shock. Proper grounding and bonding are essential for protecting people and equipment from electrical hazards. The NEC provides detailed requirements for grounding and bonding, and it is important to follow these requirements when performing electrical work. Regular inspections and maintenance of grounding and bonding systems are also important for ensuring their continued effectiveness. This includes inspecting grounding electrodes for corrosion or damage, tightening connections, and testing the continuity of grounding and bonding conductors. Any deficiencies that are identified during inspection should be promptly corrected. The electrical system is a complex and interconnected network of components, and it is important to understand how these components work together to provide safe and reliable power. This includes understanding the principles of power distribution, circuit protection, and grounding and bonding. By gaining a thorough understanding of the electrical system, you can better troubleshoot problems, perform maintenance, and ensure its continued safety and reliability. The information provided here is intended to provide a general overview of electrical grounding and bonding principles. It is not intended to be a comprehensive guide, and it should not be used as a substitute for professional electrical advice. Always consult with a qualified electrician or electrical engineer for specific recommendations regarding your electrical system. And do not attempt to perform electrical work unless you are properly trained and authorized to do so. Electrical safety is a serious matter, and it is important to take all necessary precautions to protect yourself and others from electrical hazards.